Hello, in this video we're going to recall the definition of a basis and look at several examples. So recall that a basis for a vector space V is a set, and that's very important, is a set that spans all of V, so that's important, spans all of V, and is linearly independent. And in general, those are the two conditions that we need to check. If we're given a set of vectors, we need to check, number one, that it spans the vector space, and number two, that the set is linearly independent. And if we satisfy those two conditions, we have a basis. So let's take a look at an example. In this example, we are given a set 1x and x squared. And we want to know if this is a basis for the vector space of degree 2 or less polynomials denoted P2, and this again is the set of quadratics, could be linear polynomials or constants. They all have real coefficients. All right, so to check if this is a basis, we need to do two things. First of all, let's check that the span of our set, 1x and x squared, gives us all of P2. In other words, we need to check that for any polynomial in P2, we can write our polynomial a times bx plus cx squared as a linear combination. We'll call it c1 times 1 plus c2 times x plus c3 times x squared. And that would show us that the polynomials certainly can be written in terms of those basis functions. Well, there's not much we need to do. If we take a look at the x squared terms and we take a look at the linear terms and the constant terms, we can see right away that this is possible to do. Just let C1 be A, let C2 be the B, and let C3 equal C. In other words, any polynomial, degree 2 or less, can certainly be written in terms of these vectors, 1x and x squared coming from P2. The next thing we need to check is linear independence. And what we need to check here is if we have C1 times 1 plus a C2 times x plus C3 times x squared, if that equals 0, does that force our C sub i's to be 0? Well, on the right-hand side, what we really have is a 0 plus 0x plus 0x squared, right? That is the 0 in P2. And so again, when we equate the coefficients, what we find is that if we're going to have x squareds equating to x squareds, right, this equation has to hold for any choice of x, so it must be true that C3 equals 0, and similarly equating our linear terms, it must be true that C2 equals 0, and equating our constant terms, it must be true that C1 equals 0, and this implies that our set is linearly independent. So the conclusion is that since this set spans P2 and since we have a linear independent set, this shows that the set 1x and x squared is a basis for P2. So next, let's take a look at an example that we saw in a previous video. Let's look at the set of vectors x plus 1, x minus 1, and an x squared minus x plus 2. And we want to know is this set a basis for P2? And in a previous video, we already checked for linear independence. Linear independence, and so that was done in a previous video. So the only thing we have left to check at this point is whether this set spans all of P2. Can we write any degree 2 or less polynomial in terms of these little polynomials that were given right here? Okay, so let's write this down. Let's pick any a plus bx plus cx squared from P2. And what we want to see is can we write that polynomial in terms of some c1 times x plus 1 and a c2 times x minus 1 and a c3 times the other element in our set, which was x squared minus x plus 2. Is this possible? Well, one way to approach this is to work on this right-hand side and distribute these scalars, distribute these coefficients through, and so what we get is a c1x plus c1, we get a c2x minus c2, and we get a c3x squared minus c3x plus 2c3. So let's equate the x squared terms. On the left-hand side we have cx squared, and on the right-hand side we have c3x squared, and so that tells us that c must be equal to c3. If we look at the linear terms, well, on the left-hand side we have b, and on the right-hand side for our linear terms we have a c1 plus a c2 minus c3. And lastly, for our constants, get rid of this for a moment. Constants, we have on the left-hand side a, and on the right-hand side we have a c1 as a constant, a negative c2, and a 2c3. So this gives us a system of equations, and we can look to see if there are c sub i's that satisfy. Does the system of equation have a solution or no solution? So let's put this into an augmented matrix. My columns will be for c1, c2, and c3. And of course, the particular constants I have on the one side of the equal sign are c, b, and a. So for my first column, I have 0 c1, 1 c1, and a 1. Second column for the c2s will be 0, 1, and negative 1. And lastly for c3, we'll have 1, negative 1, and 2. I won't bore you with the details, but we could certainly RREF this. Now the problem with doing that is that we're going to have to keep track of the calculations over here. And that's going to get messy. I mean, you can certainly do it, you can plow through it, but we have more machinery at our fingertips to use here. The real question is there a solution to the system? That's really what we're trying to answer. And the reason we're trying to answer that is because we were trying to see, can we pick any quadratic polynomial in P2, and can we write that polynomial in terms of the vectors we're given, because we're investigating whether those little vectors written in black here we're trying to investigate whether those span all of P2, whether they generate all of P2. Okay, so this really boils down to whether the system of equations has a solution. And you know, if we use some of our machinery that we've developed so far, we recall that if the determinant, let's call this piece A, if the determinant of A is non-zero, then we know that the system has a unique solution. And that's a lot cleaner and quicker in our analysis than trying to RREF this and keep track of all these, you know, A minus 2B or whatever it is on this right-hand side. So quick inspection, we can look at this matrix. And if we expand on the top row, we can see that the determinant would be 1 times a negative 1 first row plus third column times the little 2 by 2 obtained when we delete the first row and third column. This turns out to be a 1, a positive 1 in front. And multiplying here, we get a negative 1 minus 1. Final answer here gives us a negative 2. So that determinant is non-zero. We do have a unique solution. Now what that tells us is that we've satisfied both conditions required to be a basis. So we'll answer the question. The answer is yes.